So this is joint work with Yesem, Shu, and Mo, and they're here, and you can talk to them, and they know a lot about it. Okay, let's get going. Okay. So outline, introduction. Here we go. Implicit formula, applications to optimal transport, and here we go. Hamilton-Jacobi equations have occupied my life now for quite a lot of time in the last few years. Suddenly when I was young and foolish and I heard Crandall and Lyons talk about it, I thought this is nothing. It's just the integral of a conservation law. But boy, was I wrong. There's a lot going on here which is very different. And much more structure and a lot of interesting things. And moreover, it comes up all the time. You know, whenever in duality, for most of the things we work on, all of a sudden you're dealing with Berger's equation and things like that. So I'm going to start out with the case when there's no x dependence, ut plus h of grad u equals 0. What do we have? What's the problem with this thing? Well, the solution is non-unique if, depending on how you define solution. It is unique if you use the viscosity criterion, and you won't be surprised to find out viscosity criterion is equivalent to adding epsilon Laplacian on the right-hand side and letting epsilon go to 0. And that will pick out the unique solution. And the idea is to characterize that without going through this torture of letting epsilon go to 0. And there's a criterion due to Crandall, Lyons, and Evans, which I don't like. It's not as natural as what it is for conservation laws, where you just look at the stupid thing and the characteristic goes down. I mean, discontinuity goes down. Here it's more complicated. Anyway, so non-unique, and you want the viscosity solution. You want the limit of positive viscosity. And the solution is not smooth, which means the derivative is discontinuous. It's typically Lipschitz continuous with a discontinuous derivative. So we have to figure out how to get the good solution. And I'm going to give you a nice method that we have, but for the first time in my life, and this is 60 years of doing research, I'm going to say there might be a better method, damn it. Many of you may know Richard Tsai, who's another one of my fabulous proteges. And he has the stupidest paper, which is great. And I'll talk about it at the end of this talk. There's another way of getting solutions to Hamilton-Jacobi equations of this type in even more general type, in high dimensions, which I really like. But ours has special features that are nice, and it's still worth saving. So you heard it here for the first time. There's something you might want to use other than what I'm bragging about here. Okay, and I'll talk about it at the end. Okay. What am I doing? Wrong one. Start all over again. What did I just do? Get rid of this. I pressed that stupidly. I know, but how do I get rid of that thing on the right?
This is the mouse?
Yeah.
I don't know yet.
Okay, I know, but get rid of this thing. Okay.
I should agree.
No, I'm okay now. All right, very good. Okie dokie. So I made a career for at least 30% of my career or something, dealing with things like conservation laws and numerical methods which have discontinuities, and then we went over to Hamilton-Jacobi with Chi-Wang Shu mostly, and a lot of these are joint work with him. And these, you may have known about Eno, Weno, and all that kind of stuff, which was done here at UCLA. So these are mesh-based schemes, which means you have a grid in XY space, and therefore it's very hard to do high dimensions because the complexity and the dimensionality causes trouble. There's a formula due to Hopf. It's called Hopf-Lax, but it's mostly Hopf. Which gives you a solution if either H is convex or G is convex, or either one of them is convex or concave. It's a nice formula. H star is the Legendre transform of this thing, okay, which is being blocked by this whatever, but you know what it is. And that's a nice formula. We're going to use it, incredibly enough, in generality. Okay. But the problem with that is you have to compute the Legendre transform, and that can be complicated. And then there's a PMP, optimal control approach. But you have to compute every ODE trajectory to get anything decent out of that. But we use these ideas in what we did. There are other methods, some of which I don't like. For example, PIMs. Okay, you minimize the residual of the Hamilton-Jacobi equation and the initial condition, and you pray to God that you get a method that you can use. And it's very hard to use this in more than 3 dimensions, for example. And you can't guarantee viscosity solution and lots of other things. However, they did it, and it works sometimes. But there are other problems. And there's some other beautiful stuff, including stuff by Tingwei, who's sitting here someplace, which is a little special. Special neural net architectures that express the Hopf formula directly, and you get the answer with very little effort, but it's kind of special. Okay, that's with Darbon and Tingwei, as far as I know. So here we go. The first thing I learned before your parents were born, from Fitz-John many years ago, was how to solve a first-order, essentially a Hamilton-Jacobi equation. In a special case when H was linear, for example, but even in the more general case, you solve by using the method of characteristics. X dot is grad H. H is a function of P. P is grad U. U dot is equal to Q, which is U sub T, and so on. So the whole caboodle is equal to U dot is minus H plus P dot grad H, and P dot equals 0. These give you the method of characteristics, will allow you to continue the solution in some directions, but characteristics intersect, as you all know, and it gets complicated. And it's not global. You don't want to solve an infinite number of PDEs, ODEs, sorry. Okay. And don't be afraid to stop me. Okay. A lot of this is very familiar. Okay. Something about the slides here. But anyway, what this says is that the characteristic for x is a straight line. The x dt is grad h sub p, and the p dt is 0 because there's no u dependence. So x, the initial data, the initial value of x, you can trace it. If the characteristics don't intersect, you can trace it back to where it came from. Okay, very good. So having done all that, you arrive at the formula down below. This is a beautiful formula, which is not a big enough deal. U is equal to minus t h of p plus t times p dot grad h of p plus g of x, blah, 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 minus. The important thing about that is the first two terms cancel out very often. If h, for example, is homogeneous degree 1, or a level set problem, it's just u is exactly traced back to the initial data. Not initial data, the data at where you are. So this is an implicit method, but it's a very simple formula. So this is a major advantage when we do our stuff over dreaded Richard stuff. I mean, it's a very, very simple formula in that case. So the numerical method is easy in some cases, easier than you'd expect. Okay? And how do you do this? I'm afraid the phone. Okay. That's the formula you get. This is an implicit expression. U at time t is equal to h of p and p and God knows what, and g of x minus t. Everything. So this is absolutely implicit. U is defined by the gradient of u. And if you know anything about convergence of iteration, you don't want u to be a function of x, of u sub x, and expect it to converge when you iterate. But we do here, and it works. Okay? And one of the reasons it works, I'm learning a lot of stupid things and simple things about optimization that they should tell you when you're about, I don't know, bar mitzvah or something, when you're very young, which is that if you take a function and you want to minimize, to get the solution to an equation, you just write the equation down, you square the stupid thing, and then you do Euler-Lagrange derivative on that, and you hope to God this works. Without any, and it works if what was inside the brackets squared only vanishes when the entire thing is 0. When the gradient, when the gradient of it is 0. What am I saying? If that happens, you take a minimum of f squared. Okay, so that's equal to the gradient of that is f dot grad f, basically. Okay, and if grad f is not 0, and this is a 0 of the gradient of this whole thing, that means that the function that you were minimizing is 0 and you found the root. This is a very simple idea, but this world is full of simple ideas that don't get used enough. And that's one. Okay? So you just take the stupid thing, square it, and then do gradient descent on that. And you're in business. No questions. Okay. Very good. And it turns out that if you solve that equation that I wrote up there, equation 5, this is the Euler-Lagrange equation with the for the Hopf-Flax formula. And when Yesem told me that, I jumped and hit my head in the ceiling. It was great. That guarantees that we are getting the viscosity solution when we do this. Isn't that nice? Okay. So we're solving the Euler-Lagrange equations for the Hopf-Flax formula by stopping in the middle and zeroing this thing. Okay. And I'll talk about one alternative method I really like, which I keep plugging Richards. He better thank me, I guess. Okay. When G is convex or concave, this is the solution to the problem, because we know that that Hopf formula has the unique viscosity solution. Okay, so we saved a lot of aggravation. No question. I really like that fact. And it's almost an Evans book. Every time I tell Evans anything interesting, I wait for poo-poo. And I got a poo-poo. But then I looked at his book, and he didn't have it in the book, the little twerp. He had u at the left-hand side is equal to something whose derivative is what I have on the right-hand side. You know, and so it's a little different. Anyway, and the interesting fact is this should only work for convex things. And God help us, it works in great generality. And we don't know why. And that's interesting. In fact, it hardly ever fails, right? Okay. I got a nod. Very good. Okay. So as I said, all we do is take this thing, square it, and then use a standard artificial neural network. And then we approximate it using Monte Carlo methods. And this is one of the great things about AI, which you can't deny. You can solve crazy problems pretty easily. Essentially, it's like essentially gradient descent. If you use the right variables, the right thetas, you're in business. And that's what we did. Okay. It's mesh-free. We approximate the integral using Monte Carlo method. There's no ground truth solution. So we solved the problem solely from the initial data and knowing the Hamiltonian. And there's lots of things we can do which we haven't done. We can do inverse problems this way, and we have done some. And one of the things people really care about is trying to devise new physics by looking at solutions, by data. And in principle, we're going to try to do that. You know, find the viscosity criterion or something by looking at the solution. Or for other equations. And this idea goes beyond Hamilton-Jacobi. I'm not kidding. Take the residual, square it, and make sure what's inside the brackets is not vanishing. Okay, so here's the algorithm. Okay. I missed the first two, but you got it. Randomly sample the collocation points, calculate the Monte Carlo integration, update by gradient descent. That's all there is to it. And then eventually you get the viscosity solution. And eventually is one step essentially for things like level set method. Okay. All right. Okay, so the question is, are we answering the problems we had before? The approach is mesh-free. You don't need the Legendre transform. You don't have to compute single characteristic trajectories when you do optimal control problems. The method does not compute individual trajectories. And in fact, there's no differential equation sometimes. Okay, these are the results, and the way this is set up is not good, but anyway, trust me, we win. Okay, over and over again in terms of speed. And for example, Weno, which I would live and die by in the old days, cannot do 10 or 40 dimensions. It can barely do 3. It can do 3, and sometimes do 4. But for convex, for Berger's equation with the absolute value of x, which is an important problem, more or less almost the Eikonal equation, it works well. Okay. We know there's the memory and so on. And for concave, same kind of thing works. Is there any comments I want to make? Pins doesn't do badly, but it cannot do in the beginning, but it doesn't do well when you get to high dimensions. Okay. At all. All right. One thing about pins, I don't want to be too critical, is that what you're testing is the gradient of something, of an equation. Yep.
Any inside this is better than pin? Is that because you injected the characteristic in?
Well, pins, we have a better residual.
Yeah,
that's a big part of it.
You have a viscosity criterion almost, right?
Yeah, well, we know it's the viscosity solution because it satisfies the Hopf equation. So we sneakily go around the corner. This is really, Peter Lax just died, which is very, very sad. I knew him for 60-something years, and he was amazingly original. I mean, whatever he did was absolutely beautiful. And why am I saying this? Oh, because of his criterion for exact solution. Although I must say his criterion for the conservation law, scalar conservation law, the Hopf-Lax thing, Hopf has it. It's basically, it's much better for Hamilton-Jacobi. Not so great for conservation law. But anyway, the point being that we got the answer without killing ourselves, which is absolutely Laxian. That is, all we have to do is look at the, after you've screwed around a little bit with the Hopf formula, and you get midway through it, you stop, and then this u equals something is equivalent to the original problem. And if you solve that, lo and behold, you've solved the original problem, and you know it's the viscosity solution because of people have proven that. So I like that. Okay. We got lucky. Okay. The effect of network size. Okay. I mean, the terrible thing is I'm almost finished. I mean, this is simple stuff to explain. It really is. Okay. So what else? So we win in mean square error, for example. Look at 40 dimensions. Pins is error of 12 almost, and we know you can't do it. You can't. I mean, I defy you to take a 4-dimensional problem and grid it and do all that stuff. Okay. So this is not pie in the sky. This is useful, in my opinion. Okay. Effect of network size. P equals 2 and P equals infinity, and what did I have? Whatever it was. And you can see as the network gets bigger, unsurprisingly, a network width, you get better accuracy. And similarly with depth. Now, blue and red are two different things we're solving. So unsurprisingly, it's monotonically decreasing with dimensions in both of these things. On the left, the depth is fixed at 5, you vary the width. On the right, the width is fixed at 64 while varying the depth. Unsurprisingly, varying the network size enhances accuracy. Okay. Why do I keep doing that? Get rid of this. Here's some crazy non-convex examples. And they work. Every single case, we get the viscosity solution. At least as far as we ran it. You know, I mean, who knows? But you got to realize when we're doing what we're doing, we're really saying that you're tracing the characteristic forward or backward or something like it. And it still works, even though the characteristics have struggled their way past other ones, you know. But it surprisingly works. So there's no theorem about that at all. And I don't know if there ever will be. We haven't gotten to, have we ever got a counterexample? Not really. Not really. Well, we haven't done the most complicated possible things, but still, all these crazy functions and Hamiltonians. So you just plug this nonsense in, close your eyes, and do it. And another thing about pins, which we also do, is use automatic differentiation. And what Richard, that dog, does is replace, he views the entire thing as a continuum, and then he sets up a grid which is continuous and just gets derivatives by saying u of x plus h direction, one direction, minus u, and so on, without a grid. And the principle is continuous. And what I'm giving you the punchline. And what he also does, which is amazing, is add Lax-Friedrich viscosity. How many of you know what that is? What kind of audience is this? I should give a course on I think we're going to change the world of numerical PDE, because people using AI, which is an incredible tool, don't know numerical PDE in a lot of cases. And that's a terrible thought. What I suggest you guys do is read Chi Wang Shu's notes or something.
Is that the expansion?
What?
Is that the expansion?
The expansion.
So you get by expanding Lax.
Yeah. Yeah, basically. It's always, I mean, it's adding viscosity, which is h times Laplacian. Very simple. And a big enough constant in front of h. That's all you need. But you could have done one of my crazy upwind schemes with looking to the left and twisting your neck or something, and that would have worked also, probably. The fact of the matter is, what he noticed is that you write down the Hamiltonian, the discrete operator, and that is invertible. Isn't that cool? So when you take it squared and take its gradient, you're guaranteed that you've solved the numerical method. That is amazing. And I heard somebody gave a lecture in my seminar, one of his colleagues, whose names I forgot, unfortunately, a young guy, and I fell asleep through it in my arrogance. And it wasn't until I gave a talk at Beers and somebody was harassing me as who is this obnoxious person? And it turned out to be Richard. And he was right. But we can do things he can't. But he can certainly do things we can't. Like not worry at all about convexity. At all. But he only gets first order accuracy, which isn't bad in high dimensions, you know. So the moral of the story is you take the Hamiltonian, I'm plugging his stuff, which I will definitely go to heaven for. You know, it's, you take this finite difference, continuous finite difference scheme, you square the stupid thing, and then you use least squares, more or less, to get the answer. And it works. There's a lot of things you have to do to make sure it works. You know, you have to get there slowly and so on. I have a feeling it's going to be much slower than ours in some cases, but it's worth looking at. And I don't know. I was once talking to, who was it? I think it was Lax, and he said, you know, I really like what you showed me, which means I want to steal it. And that's, I can't read Richard's paper without wanting to jump in. So anyway, that's all I'm going to say about it. Enough. Okay. Very good. So here are these examples. I'll keep doing that, sorry. And here are numerical solutions, which I like because you see sharp corners coming, which means we are getting the viscosity solution for these non-convex things. And that's a big deal, okay? Without any special treatment. You can see it as a, for capital T is the interval in which we're working. And it nicely gets there. Now here's the iconal equation, which is instantaneous. I mean, that's really fast. It's just a formula, u equals this, period. Because the characteristic goes all the way back. Okay. So that's the pièce de résistance. Okay, now what we're doing is optimal transport. Let me go backwards. I can't believe we missed the beginning of this. Can I go backwards? Yeah. What happened? God, I did something. I can't be trusted with this thing. Okay. Okay. God, I'm missing the slide, which has, let me go back. Let me go again. Oh, yeah. Okay. I told you before, when you're doing things like the iconal equation, which we are doing now, when we do optimal transport, I skipped something, but anyway, you wind up doing a forward map and a backward map, and the two trivial maps. You just update what you get, and you don't have to iterate. And you have a deep learning framework for optimal transport based on the characteristics. Learn the viscosity solution for a neural network. Use theta to approximate the viscosity solution using the implicit solution formula of the HJ equation. Okay. Now let me go. And you recover the optimal transport map. There it is. And without numerical integration of ordinary differential equations. So this is what the competition would do. If you use a dual formulation, you're not guaranteed optimality of T. You don't know it's going to be the entropy, not the entropy, the viscosity solution. If we use a dynamical model, you have to do iterate. And we don't have to. It's one step. Okay. And the Hamilton-Jacobi method is bidirectional and direct, and you get the right answer. So this is a case when we clearly win. So for optimal transport, I recommend it. Better than a competition. Okay. And that's a very important problem. That it comes up all the time. And Hamilton-Jacobi comes up all the time because of duality. And so again, I mean, my suggestion to young people is learn numerical analysis of Hamilton-Jacobi equations. It seems a little special, but it's worth it. And one of the best references is probably Chi-Wang Shu writes great notes about nonlinear hyperbolic equations, numerical solutions. Now you can look at Levesque's book, but it stopped. And just when it got interesting, it stopped. Okay. Very good. So here are examples. This is, what's it called? Something transport. Give me the buzzword. When you transport color. Oh, this is target distribution. We haven't got that yet, sorry, target distribution. Okay, so on the left is the target distribution, and on the right is the source distribution, and this is what we get when we go from target to source, SOURC. And I'll give you a hint. The one on the right is ours, which is the best, of course. That's ours. And the third one on the right is pins, which isn't that bad, but you can see that the characteristics, if you look carefully, you'll see the characteristics cross when they transfer from one guy to another. And the one on the right, the characteristics do not cross, and they get there. Okay. They get there in essentially one step. Okay, let me go down. Okay. And here is source versus target.
Seems you have no crossings at all.
What?
Seems you have no crossings. At least
No crossing at all.
Oh, you may have some.
Wait a second. Did I?
In the pin, there are some.
Yeah. But your loss function, you only penalize the forward one, you penalize forward inverse both.
We penalize forward and inverse because we can do it, but they don't. Okay. And so it's more expensive. And maybe pins cost, it doesn't cost, I don't know. I convinced myself it did. And the one on the right is not supposed to cross. Okay, so don't look at it. No, I'm kidding. Okay. Okay. And here's the accuracy of learned transport map in Gaussian to Gaussian setting, where you have a closed formula of the know the closed formula for the optimal transport. Okay, and here's a L2 error across optimal transport, and we do well. Okay, and again, we don't womp pins, but we're better. And they managed to do high D because they knew the answer. So they use that information. Okay.
So assume you use the same network for different dimensions, the same size of network.
Yeah.
But do you get a chance to try to keep the same accuracy? You may have to exponentially increase the architecture, the size
That's
of
what
network.
he showed for the former Hamilton-Jacobi equations, for when he just shows some.
And we did that before, I think.
So definitely, once we increase the network size, then we can obtain the better results. But for the better comparison with baseline models, we just keep size
Yeah, I'm curious about
Well, our accuracy goes down with
the
D.
complexity, right? Because you're showing how many Jacobi you try different Hamiltonian and the different initial functions.
Yeah.
So if you use a random network, right? If you approximate a high dimension function, it's going to exponentially depend on
Yeah,
dimension.
and they will be presented in the next slide.
I see.
He will present some memory transmission and computation time.
Oh, good. I'm managing 40 minutes is good. Okay. And MM wins, but that's has a lot of other problems. Okay, I won't go into it. Sometimes, in very high dimensions. But we don't have a problem with high dimensions. Okay.
What is MM?
MM? What is MM?
It's this MM stands for max min. So they are based on the dual formulations.
Oh, I see.
They need to solve the max min on
Yeah.
virtual layer training.
Okay.
Yes.
All right, what else have we got here? Let me go down. Training time per epoch, okay. And we win, we're red, versus other methods. Look at the one on the left, for example.
This is still for the same network, different dimension. But
Yeah.
to achieve the same accuracy, you might have to increase the
Yeah, that's
network
true.
size dramatically for the high dimension.
Yeah, but it works at least, it converges. Okay. And again, I mean, we don't know the solution at all, you know, which is not always the case in some of these methods. Okay. This is a fun example. This is color transfer. This is where Shu and Mo came in. Learn an optimal transform map between the color distributions of the source and the target images. RGB are samples from probability measures. And we are on the right. Okay. These slides should be changed a little bit. Okay. Let me go down. And ours is the one on the right. And if I can go backwards, which I can't, maybe I can. I don't know. How do I go backwards on this thing? Can I go backwards? Where's our... That one, maybe.
Maybe this time.
Ah, you're a genius. Okay.
Is that the slides you want to show?
Yeah, exactly.
Maybe you
Okay.
do this. Or you
Oh,
do this
very
one.
brilliant. Okay, I should have done it 40 minutes ago. Okay, so we are on the right, and you can see that we do very well. And the other guys are not disasters, but ours are better. Okay, for this method. And it's relatively fast. Okay, anything else? No. Okay. Very good. Color transfer, and here are the numbers. Doesn't work over here. I'm trying. Oh, now what do I do? I should not be allowed to be anywhere near computers. Oh yeah, there you go. Okay, now very good. Okay. And our accuracy across 3 data sets wins against these other methods. Okay, very good. Now we're going to go down. Okay. And here's MNIST. If I can do it. No. On the left is 0, 1, 2, 3, 4, and we want them to go 5 through 9, and we do well. If I can show it, I can't show it. Okay. Very good. And the one on the right is competition, not as good. No, forward, backwards, sorry. So here's the conclusion, after 40 minutes. We have a novel implicit solution formula for Hamilton-Jacobi is derived from characteristics. We get the Hopf formula in convex and concave settings by eliminating Legendre transforms. We have a simple deep learning method for solving it, mitigating the curse of dimensionality. We demonstrate the scalability of the proposed method across high-dimensional non-convex benchmark problems, and show that the implicit formula together with characteristic flows gives you a good way of solving optimal transfer problems, which was one of the best things coming out of this. And that's it. And the next one is probably references. And we didn't put Vicious in here because we just found out about it. But here are some very good people, some of whom are sitting here, Tingwei. And other people we know, like Jerome, and Wei King, and Wilcox. And so this is a hot area. I like it because it's definitely applied. People are going to, if you do anything good, people are going to use it. And second of all, if you really know and feel good about numerical analysis, you're in business here. And because a lot of the people who do this stuff do not have that feeling, in my opinion. So that's probably it. Thank you.